Hello and welcome back to some more examples in the stiffness method. Once again, an example using a beam that is suitable for an exam style question. And this is the exam question we will be solving in this session. As you can see, it's a beam, it's fixed on either end, and it has a point load. We are told that EI is constant throughout, and we also know that we can ignore axial deformation. In other words, this is axially rigid, and we can use the relevant stiffness matrix. What we need to find is the displacement and the rotation under the point load. We'll do this now step by step, and you can follow along in each step. If you are a little bit rusty on the theory, go back and listen to the theory lectures, but if not, let's get to it. As we already saw, this is the question that we need to solve. We've got a beam that is fixed on both ends, and there is a point load applied at 6 meters from the left-hand side. Assuming these points are A for the fixed support at the left, B where the point load is, and C on the right-hand support, we can see that the beam is divided really into two parts of 6 meters and of 4 meters. We know that EI is constant throughout, and we've also been told to ignore axial deformation, which means that we can use the smaller 4x4 stiffness matrix for each segment of the beam. And we've been asked to calculate the deflection and the rotation at point B. Now, two things to consider. The first thing is that we will need to divide the beam into two parts, AB and BC. The second thing is that the local coordinate system matches the global. So we will not have to rotate. Okay, that'll save us a bit of time in the exam. So we start off by calculating the stiffness matrix for AB. And let's do that in dark green. As we said, we're going to use the 4x4, and that means that we have EI and then all the members. So 12 over L1 cubed, then we have 6 over L1 squared minus 12 over L1 cubed, 6 over L1 squared, and so on. With L1 being 6 meters. Now what I should have done before, and I will do that now, is I am going to just note where those degrees of freedom are. So I have 1, 2 here, 3, 4 here, and 5, 6 here. So those are the degrees of freedom that I'm solving for. And the best thing to do is once you have a stiffness matrix is to add those degrees of freedom. You'll see that this will become really helpful. So these columns correspond to these degrees of freedom, 1, 2, 3, 4, and these rows also correspond to degrees of freedom, 1, 2, 3, 4. Now that we have KAB, or the stiffness matrix for the first beam, we're going to do exactly the same for the second beam. So KBC equals EI once again, and I'm just going to write out all of the members of this second stiffness matrix in much the same way. And in this case, L2 equals 4 meters. And once again, I am just going to write down the degrees of freedom. Now in this case, if we have a look back at our beam, we can see that beam BC has the corresponding degrees of freedom of 3, 4, 5, 6. So adding them in, 3, 4, 5, and 6 for the columns, and also 3, 4, 5, 6 for the rows. And that's it. I have my two stiffness matrices for each of the beams that need to make up this full stiffness matrix in the local coordinates, which are also the global coordinates, so no rotation needed. Now, as we already mentioned, no rotation needed because the local system is the global system. And I just want to show quickly how these all match up. So if we scroll back up, we can see that point B is the joint point. So AB has degrees of freedom 1, 2, 3, 4. BC has 3, 4, 5, 6. So 3 and 4 are those shared degrees of freedom. And that means that if I were to draw my stiffness matrix, so this would be my first one with 1, 2, 3, 4 degrees of freedom. And then I draw on my second, those degrees of freedom here, 3, 4, 5, 6, meet up. Okay, so that is also 3, 4, 5, 6. And here that would be 1, 2, 3, and 4. And so this area here is where degrees of freedom 3, 4 will add up from beam 1 and beam 2. Let's just create that full stiffness matrix in case we're asked. Now, in this particular exam question, we haven't been asked, so you can see how we might skip that step. But just in case we are asked, let's go through this. So my stiffness matrix is going to be, let's see, EI. And now I'm going to add in all the different parts of the matrix. So from my first matrix, I've got 12, and I'm putting in the lengths as well, over 6 cubed. Then I've got 6 over 6 squared. Then I've got minus 12 over 6 cubed, and then 6 over 6 squared. And I don't have anything in these places. Because remember, this global stiffness matrix has all the degrees of freedom included. So just zeros where there is nothing. And we just continue to fill it in for beam number 1. And that's it. I've added all of those members from the stiffness matrix from the first beam. Now I need to add on top of that everything from the second beam. And as we recall, 3 and 4 are joint. So starting off here from 3, 3, plus 12 over 4 cubed this time, and here I've got plus 6 over 4 squared. Here I've got minus 12 over 4 cubed, and here I've got 6 over 4 squared, and just continuing in exactly the same way. And that's it. This is the full stiffness matrix. Obviously, we can calculate what everything is. I'm just adding the degrees of freedom because this will continue to come in handy as we continue. Now, the next thing that we're going to want to find is the load vector. And our load vector, F, is really all the external loads. Now, potentially we have external loads at each of those points, A, B, and C. So generally it would be Fy, so the vertical load at point A, then potentially a moment at A, then a load at B, a moment at B, and then a load at C, and a moment at C. However, in our case, we know exactly where the load is. We just had, if we scroll back up to the start of the question, a load of 20 kilonewtons at point B. Now it is a load, it is a vertical load, it is in the direction of degree of freedom 3. So really I have 0, 0, minus 20, because it's in the negative direction, and the rest are zeros. The next thing I need to configure is my displacement vector. And much in the same way, my displacement vector d, which I don't know, I'll need to solve the equations to find it, but it is built out of a vertical displacement at A, a rotation at A, a vertical displacement at B, a rotation at B, a vertical displacement at C, and a rotation at C. Obviously, these things are currently unknown. And now that I know what everything looks like, I can look back at my stiffness equation, which is the stiffness matrix times the displacement vector equals the load vector. And obviously, what I don't know, what I'm looking for is this D. So if I write this out, I have
a stiffness matrix. Let's add on the degrees of freedom, multiplied by my displacement vector, and that should equal my force vector, which, as I said, I only have minus 20 here. The rest are zeros. And that is what it looks like. However, there is another thing that I know. I know that A and C are fixed, and therefore I know that VA equals the rotation at A equals VC equals the rotation at C, and they all equal 0 because these are all fixed. And that means that I can eliminate those degrees of freedom, the corresponding rows and the corresponding columns, from my calculations because they're just going to give me zeros. So taking out those two rows, so rows 1, 2, 5 and 6, and then the corresponding columns, so 1, 2, 5 and 6. And this leaves me with what I need to solve. So here, this bit here, then this bit here, and this bit here. And so I can see that from the stiffness matrix, I only need columns and rows 3 and 4. And if I go back up to where I wrote everything out, I can see that it's pretty easy to take out. Just because I've labeled everything neatly, I can see that this is the bit that I need for the solution. So let's write everything out neatly and solve the equations. So what I have is I've got EI, this is the bit of the stiffness matrix that I need, and I had here 12 over 6 cubed plus 12 over 4 cubed, and then here I had minus 6 over 6 squared plus 6 over 4 squared. Then I had here minus 6 over 6 squared plus 6 over 4 squared, which obviously is on the diagonal, so they have to equal. And here I've got 4 over 6 plus 4 over 4. And I've just put that into my calculator so that I can write everything out pretty shorthand. So I've got EI, and here I've got 0. If you just calculate it, 243, 0.208, 0.208, and 1.667, multiplied by VB and theta B, which, by the way, is exactly what I'm looking for, and that equals minus 20 and 0. So I can see that from here I will get two simultaneous equations, and we can write out those equations and solve them. So the first equation I get from the first row, so not forgetting my EI, is 0.243 VB plus 0.208 theta B, and that has to equal minus 20. And my second equation is EI 0.208 VB plus 1.667 theta B, and that equals 0. So I can divide in the first one both sides by EI, so that goes, and here I have 20 divided by EI. And also in the second equation I can divide by EI, and that just goes because dividing this side by EI is still 0. The easiest way to solve this, I think, is taking equation 2 and isolating VB. So if I take that equation, 0.208 VB plus 1.667 theta B equals 0, and isolate VB. So VB is minus 1.667 theta B divided by 0.208, and that gives me minus 8.012 theta B. I can take that and I can sub into equation 1, and if I do that I get 0.243. Instead of VB I introduce minus 8.012 theta B, and then I've got also plus 0.208 theta B, and that all equals minus 20 divided by EI, and that gives me minus 1.739 theta B equals minus 20 over EI, and so theta B, which is the rotation at B that I'm looking for, equals 11.5 divided by EI. And that is the rotation, one of the things I was asked to find. And the second thing I need to do is just substitute that back into VB. So VB, the vertical displacement at B, equals minus 8.012 theta B, and that is minus 8.012 times 11.5 divided by EI, and that gives me VB equals minus 92.13 over EI. And that is the vertical placement at B. So both of the things that we needed to find. And that is the end of this specific exam question. Obviously, it could have continued and asked us to find internal forces and other things. I think in a time-bound exam question, this is probably enough to get your head around in a very specifically allocated period of time. And that's it. I hope you found it useful. Practice and ace your exams.